In this example, it looks like we have an initial value problem, and we know the differential equation and the initial value. And first of all, it's asking us to show that these two functions are solutions. So in general, how do we check if something counts as a solution or not?
If you can plug it back in and still get the same grid.
Yeah, we want to plug that in to the original differential equation and make sure the equation is still true, which means, of course, we'll need to find y prime. So let's try that. So we start by saying let y equal 1 minus t. Then what would y prime equal? What would be the derivative of that function?
Would it be -1?
Yeah, the 1 goes away because that's a constant, so we just get derivative of negative t, which is -1. So we'll want to plug in that y value and that y prime value into the original differential equation and see if it still works. So let's try this. If we take a look at each side of the equation independently, we know y prime is going to be -1. And then if we take a look at the other side of the equation, we have, if we just copy this down exactly as is, negative t plus square root of t squared plus 4 times, and now we'll want to replace y with 1 minus t, all over 2. So this whole thing over 2. And if we can simplify that and show that it just equals -1, then we're done. That shows that really is a solution. So to simplify that, we got negative t plus square root of t squared plus 4 minus 4t. So t squared minus 4t plus 4, all divided by 2. Can we factor t squared minus 4t plus 4?
Would it be t minus 2 squared?
Yeah, which is very convenient because if it's t minus 2 squared, then we take the square root and the squared just cancels it out. So we end up with negative t plus t minus 2 divided by 2. Simplify that and what happens? We've got, negative t plus 2 plus t cancels out. Minus 2 divided by 2 is -1. And that's exactly what we have on the other side of the equation as well. So yeah, -1 equals -1 is a true equation, which means, yes, this really is a solution. At least it's a solution to the differential equation. We also want to show that it fulfills the initial conditions, because we want to show that it's a solution of the entire initial value problem. So to show that it fulfills the initial conditions, we can just replace t with 2. 1 minus 2 is -1, which is exactly what it's supposed to be. So this function makes the differential equation true, and also it passes through the point 2, -1. So yes, this y1 really is a solution to the differential equation. And then we could do the same thing with y2. We could take the derivative of negative t squared over 4, plug it in, the derivative and the function itself, and we should get that this equation is still valid. It still makes these two sides equal. And then likewise, you could plug in 2 for t and -1 for y. 2 squared would be 4, over 4 is 1, -1 equals -1. So it looks like y2 also fulfills the initial value, and you can try plugging in the function and its derivative into the differential equation as well. Any questions on that so far? So we can verify that both of these really are solutions. And I'm skipping the actually plugging it in and running the algebra for now, because I think that's going to run pretty much the same way. But for the idea of the existence of two solutions, this is really, I think, the heart of what this question is really getting at. We now have an initial value problem with two different solutions. What does the existence and uniqueness theorem claim about an initial value problem, though? If you've got a differential equation and an initial value, how many solutions should you expect?
One unique solution?
Yeah, typically we expect one unique solution for the initial value problem. Ideally, the differential equation has many solutions, but only one of them passes through that point, that initial value. So we've got a problem here. We've got two different solutions that both pass through that same initial value. So we got to be careful about checking this with the existence and uniqueness theorem. The existence and uniqueness theorem says if some conditions are true, then you get one and only one solution. Clearly, we don't have one and only one solution here because there's two solutions. But what's the if part of the existence and uniqueness theorem? What's the requirement there? Yeah, if the function of t and y and its partial derivative with respect to y are continuous, and specifically not just at that location, but continuous on some region, usually some rectangle containing t naught comma y naught, then the initial value problem y prime equals f of ty, y of t0 equals y naught has exactly one solution on that region. So in order to conclude that the then part is true, which it isn't in this case, we'd have to know that the if part is true. So let's check the if part. We want to know, is it true that this function and its partial derivative are continuous on some region that includes this point? So what happens if we try that? If we take if we try this function and we plug in 2 for t and -1 for y, what happens?
It should still work out and be continuous.
Yeah, because if you plug in 2 for t, you get 4 here, plus 4 times -1 for y. So 4 plus -4 is 0. So it seems like that should work. This point does not lead to a discontinuity. But what happens if we're just barely over that line? What happens if y is any more negative than that? Like if it was t equals 2, y equals -1.001.
I tried getting the interval, and what I got is that y has to be less than 0.
What do you mean less than 0?
Because I did t squared plus 4y has to be greater than or equal to 0. And then from there, I got like t has to be greater than or less than to 2 square root negative y. So then I said negative y has to be greater than 0 or less than 0 to cancel out the negative.
Or we could just solve for y, I think. It might actually be easier to solve for y because then we wouldn't need to worry about the ambiguity of the square root. If you isolate y here, what would you get?
Negative t squared over 4.
Yeah, and since we're not multiplying or dividing by any negatives, we keep the greater than or equal to sign. And does this point make that inequality true? if we actually plug in 2 for t and -1 for y. If we actually try that out, if we plug in -1 for y and then plug in 2 for t, what's -2 squared over 4?
And it'll be -1.
Yeah. Is it true that -1 is greater than or equal to -1?
Yes.
Yeah, that is true. But keep in mind it's on the borderline, right?
Mm-hmm.
It is true that -1 is greater than or equal to -1, but just barely. If this y value had been any less, then this would not be true. So we got to be careful about this region of continuity here. This 2, -1 is in a region of continuity, but it's on the edge of the region of continuity. The if part doesn't really say anything about being on the edge or not, but that does seem kind of suspicious. And of course, we also need to check not only the function itself, but what else needs to be continuous.
The derivative?
Yeah, so let's check the partial derivative as well. Technically, this initial value does make the function itself continuous, but then since it's right on the edge, that makes me suspect something more might be at work here. And in fact, if we check the derivative, if we try the partial of f with respect to y, this over 2 we can deal with later. We can just take the whole thing divided by 2 since that's a constant. But this -t here, what's the derivative of -t with respect to y? If we're taking the partial with respect to y, what are we treating t as?
The constant.
Right. And derivative of a constant would be?
Then it will be 0.
Yeah, that's 0. So we're going to have a 0 plus whatever we get for the other part. And let me fill in the divided by 2 at the end so we can make sure we don't forget that. Now for this square root, we probably want to treat that as an exponential. The square root of t squared plus 4y is the same as t squared plus 4y to the 1/2 power. And how would you take the derivative of t squared plus 4y to the 1/2 power? First of all, yeah, we're going to have to deal with the chain rule. So we'll take the derivative of the outermost function, to the 1/2 power, ignoring everything inside for the moment. So let's just ignore what's inside for the moment. And we just say we've got something to the 1/2 power. What's the derivative of something to the 1/2 power?
Is it just the derivative inside above the square root of the original portion?
Yeah, well, forget about the chain rule for the moment. We just got something to the 1/2 power. If this was just like y to the 1/2 power, what would be the derivative of that? What would you do with that exponent?
Move the exponent down and then so -1 on the exponent.
Yeah, so we've got the 1/2 as a multiplier, and then we'd have whatever's left, whatever's inside to the -1/2, because we'd be reducing the exponent by 1. So we've got 1/2 from bringing the exponent out as a multiplier times whatever's inside to the -1/2, because we're reducing the exponent by 1. Now let's take a look at what's actually inside. What's inside is that t squared plus 4y. And now, as you mentioned, we have to use the chain rule as well, because the derivative of what's inside is not just y. So what is the derivative of what's inside with respect to y? Right, we just have an extra 4 from the derivative. So this whole thing, or this piece, gets multiplied by 4. And I'm going to just go ahead and put that in the numerator of this fraction. We'll call that 4 over 2. So 4 over 2 times t squared plus 4y to the negative 1/2, all divided by 2. Any questions on applying the chain rule there so far? So let's try simplifying that. The 0 doesn't matter, so we just have 4 over 2, which is 2, times t squared plus 4y to the negative 1/2 divided by 2. So that just cancels out the times 2 over here. And what does to the negative 1/2 power really mean?
There's a square root on the bottom.
Yeah, negative 1/2 means 1 over square root. So we really have 1 over square root of t squared plus 4y. And what happens if you plug in 2 for t and negative 1 for y here? T squared plus 4 times negative 1, what do you get there?
Oh, it would be 0.
Right. And since this is in the denominator, that's now a problem. Just having 0 inside of a square root is fine. But if you've got 0 as the denominator, square root of 0 is 0, so we get 1 over 0. That's a discontinuity. So what we can say here is at this point, f of ty is continuous, but the partial derivative is not continuous. So that means we cannot say that the if part is true, and therefore we can't guarantee that the then part is true. We do have solutions, but those solutions are not unique. There's several solutions, in this case, 2, at least 2. Maybe there's more, we haven't checked. But that's really the issue here, that the existence and uniqueness theorem only applies if the entire if part is true. In any situation where the entire if part is true, you can guarantee that the then part is true. That's really what an if-then statement is all about. In this particular case, the if statement is not entirely true, so we can't guarantee the then statement at all. Any questions on that so far?
I'm just kind of maybe confused on, because the problem mentions that it doesn't contradict the theorem, but in this case, like we just proved it that it does.
Well,
so,
it doesn't. Contradicting the theorem would mean that you find some situation where the theorem is false.
Mhm.
An if-then statement can only be false when the if part is true, but the then part is not true. Like, for instance, if I said, if a shape is a triangle, then it has 4 sides. That's false because you can show me a triangle that makes the if part true. It is a triangle. And you can say, but it does not have 4 sides, so the then part is not true. So you can only show that an if-then statement is false by providing an example, a counterexample, where the if part is true, but the then part is not true. Is this a situation where the if part is true, but the then part is not true?
I think this is like the if part is not true, and then that's why the then part is also not true.
Right, or at least it doesn't guarantee anything about the then part. Maybe the then part would be true, maybe not. But the idea is an if-then statement only even applies to situations where the if part is true. If you're looking at a situation where the if part is not true, the if-then statement doesn't tell you anything about it at all.
Let's see. Okay.
So I would say that this doesn't contradict the theorem because the theorem doesn't apply to cases like this anyway. The theorem is only talking about situations where f and df dy are continuous at the initial value. Since this initial value problem is not one of those situations, that means the existence and uniqueness theorem doesn't make any claims about it at all.
Okay, yeah, that makes a lot more sense, yeah.
And that's a very important thing to keep in mind about if-then statements. If-then statements are claiming a very specific thing. They're claiming in all situations where the if part is true, we can guarantee that the then part is also true. And you don't want to accidentally try stretching that to mean too much. The if-then statement doesn't say anything at all about situations where the if part is not true. And if the if part is not true, the if-then statement doesn't really claim anything. Any other questions on that so far? And then B, I think, is just generalizing it. We want to show that this family of functions in general, anything of the form ct plus c squared, where c is some constant, is a solution. And again, you can show that just by plugging it in. This isn't really saying find the solution of this differential equation. It's saying here's a solution, plug it in to show that it really is the solution. So you could do this by just taking this function and its derivative with respect to t, plugging in the function for y over here, plugging in the derivative for y prime over here, and again, show that the two sides of the equation both result in the same thing. If you can do that, you've proven that, yes, this is a solution to that differential equation. And the thing is, I think what part B is getting at is that y1 is of this format. You can get y1 exactly just by replacing c with -1, as it says in the parentheses here. But there's no c value you can plug in, no constant you can use for c that results in -t²/4. So I think what part B is getting at is that ct plus c squared is a general solution to this differential equation, except it's not truly general because we've found a solution that doesn't fit that format. And the reason for that is that this solution is talking about points on the boundary line where the where the partial derivative becomes discontinuous. So this general solution works for most cases. It works for all cases where the initial value is on a region of continuity. But if you're talking about an initial value on a point of discontinuity, anything goes. It doesn't have to fit that format. It doesn't even have to have a solution at all. Any questions on that one? Or any other questions on this existence and uniqueness theorem stuff? All right, then let's take a look at that idea of using positive versus negative values for the phase line, for figuring out where an autonomous solution is going to have equilibrium values.
I mean, I have a problem just similar to this. It's like that has the idea. You want me to send that in the chat?
Sure. Okay, this one here?
Yeah.
And we're just trying to figure out what sort of equilibrium values we have and where they are?
Yeah.
Okay, which one would you like to try out?
I would like to try out part C. That's what I was struggling with.
Okay, where we've got these unknown coefficients, but we at least know they're positive. Well, yeah, let's try that out. So we have, let me just copy that down and we'll start a new blank page. Okay, so our differential equation is ay minus b times square root of y. And we want to figure out where do we have equilibrium solutions. So to find that out, we want to look at, first of all, just where is y prime going to be 0? Because Because if y prime is 0, that means we have a flat line. If we have a specific y value that makes y prime 0, then if you start at that y value, you've got a 0 slope, so it's going to be flat, which means you stay at that y value. And since it's still the same y value, the slope is still 0, so you continue to just go flat. So that's what you want to look for. For equilibrium solutions, replace y prime with 0 and solve for y. So let's try that. So let 0 equal ay minus b square root of y. And how would you solve that for y?
Divide by root y on both sides?
Maybe. The problem is if you're dividing by root y, what are you assuming about root y?
Oh, that it's greater than 0?
Yeah, or at least that it's not 0. So you got to be careful about that. If you're dealing with, if you're dividing both sides by an unknown value, you've got to take into account the possibility that maybe that value is 0. So before we do that, let's check, is it possible for y to be 0? If you just plug in 0 for y, does that make the equation true?
Yes.
Yeah. Y equals 0 is a solution. So let's check what about other solutions. Suppose y is not 0. If y is not 0, because we've already covered the 0 possibility, as long as we're explicitly saying we're assuming we're looking for non-zero values of y, then we can divide by square root of y. Yeah, that's another way you could do it. You could try factoring out square root of y. If you factor out square root of y, you get square root of y times, and what's left there? If you factor out a square root of y, what does this become?
A root y minus b?
Yeah. Because y can be written as square root of y times square root of y. We're factoring out one of these square roots of y, and we're left with a times square root of y. And then b, we're just factoring out the single square root of y that shows up there. And note that this part is exactly what you get if you divide both sides by a square root of y. With the factoring approach, though, we would just say we would use the zero product property, that if two things multiplied equals 0, then one or the other has to be 0. So we could say square root of y equals 0, or a times square root of y minus b equals 0. And if square root of y is 0, then of course we just get y equals 0 by squaring both sides. If instead we have a square root of y minus b equals 0, how would we solve that for y?
Add b divided by y and then square it?
Yeah. So b and divide by a. And yeah, then we could just square both sides. So b squared over a squared. So that's our other equilibrium solution. Or you could write that as b over a squared. Either way works. And we don't know what those values are, but we at least know this is going to be positive. Because, well, we're assuming a and b are positive, but also we're squaring it anyway, so the result is guaranteed to be positive. So it looks like that's our equilibrium value. We know that, and we could set up a phase line here. If we just imagine this is a single cross section of the direction field, we know we have important values at 0 and b over a. So if you think of this as just like the y-axis, a stylized view of just the y-axis, or any single column of the direction field, we know we've got something important going on at y equals 0 and y equals a over b. So I'm going to mark those. y equals 0, y equals a over b. And this is kind of arbitrary. I'm just drawing in some lines to call 0 and a over b. Or b over a squared. So we know these two values both count as equilibrium values. And let me mark those. We know this is equilibrium. This is also equilibrium. But we'd like to know what type of equilibrium and what's going on in between those. So first of all, we can check the value of y prime in the in-between regions. We know at these 2 points, y prime is going to be 0. But everywhere else, y prime is going to be either positive or negative. So let's check that. In the region, let's say the region below 0. If you plug in a value below 0 for y, what happens?
It can't be below 0, right?
Yeah, we've got this square root of y, so negative values for y don't work. So we can actually ignore everything below 0 because that's undefined anyway. So I'm just going to cross out everything below 0 and say that in this region, y prime is undefined. So we're not even going to consider that region. But if we take a look at the other regions, let's say we're talking about very large values of y. If y is an enormous value, would you expect ay or b squared of y to be larger?
You expect ay to be larger?
Yeah, ay is going to be larger than anything times square root of y, as long as y is large enough. There's going to be some critical point where y is going to be larger than square root of y as long as y is greater than 1. There's going to be some, but the a and b values influence it also. But there's going to be some critical point where the values of a and b don't really matter because y is big enough to overwhelm that. And it turns out that critical point is exactly b over a squared. So anything above that, ay is going to be so much larger than b square root of y that the result is positive. So we know in this entire region, we know that y prime is positive, which means we have the function is increasing. And what about in the region between them? If y is small, like if you imagine, and we could try plugging in some values here, like maybe b over a squared divided by 2. That'd be a good value to plug in if you want to do this algebraically. But perhaps a more conceptual approach, if you imagine plugging in a number very close to 0, what would you expect about to find about ay versus b square root of y? Which one of those is going to be larger if y is very small? Yeah, the square root of y term is going to be larger. And you can actually see this if you try taking square roots of specifically numbers less than 1. Like if you imagine just a and b are both 1 for simplicity. If you take like the square root of 1/2, the result is actually going to be larger than 1/2. I think this is probably easiest to see with like 1/4, for instance. What's the square root of 1/4?
It'd be a half.
Yeah, square root of 1/4 is 1/2. And that is larger than the original 1/4. So if y is smaller than 1, then square root of y is actually going to be larger than y itself. And more specifically in this case, no matter what b and a are, as long as y is less than b over a squared, then b square root of y is going to be larger than ay. So we get a negative result when we subtract small number minus big number. So in this interval between 0 and b over a squared, we can say that in this region of y values, y prime is negative. So y is a decreasing function. So we know everything about the sign of y prime. In this region, y prime is positive. In this region, y prime is negative. At these equilibrium values, y prime is 0. And everywhere below 0, y prime is undefined anyway. And I think it would be useful to actually draw in the arrows that we usually use on a phase line. Y prime is positive, so y is an increasing function in this region. Y prime is negative, so y is a decreasing function in this region, which immediately tells us what type of equilibrium do we have here?
Unstable?
Yeah, it looks like all the solutions nearby are diverging away from that value. So we would say this is unstable equilibrium. And what about the y equals 0 point?
Can we say it's stable even though it's just one side going?
Yeah, I think I would call this stable, because stable means all the solutions nearby are approaching it. The solutions nearby above it are approaching it. The solutions nearby below don't even exist, so we don't need to consider them. So I would call this stable equilibrium. So we've categorized the equilibria as stable versus unstable. And we know everywhere where the function is increasing, we know everywhere where the function is decreasing, we know where it's undefined, or at least where y prime is undefined. We don't really know whether there's a solution in this region or not, because the existence and uniqueness theorem falls apart. All we can say is we can't guarantee that there's a solution in this region. Maybe there is, maybe there's not. I'm guessing probably not. But all we can say for sure is it's not guaranteed. Any questions on that so far?
So even if there's a region that is undefined, we can still, if we look at certain portions of the, it's just like another portion of the graph that is defined, we can just say whether or not it's stable or unstable. Like if it's, let's say that arrow above y equals 0 was like flipped, then we say that's an unstable equilibrium.
I think so, yeah. You might want to double check on exactly how the professor wants to define stable versus unstable equilibrium. But what I'm seeing is if we were to graph this, we've got these asymptotes at 0 and negative b over a squared. What the solution curves are going to look like, I would expect, would be something like, we know it's going to be diverging away from this asymptote and approaching this asymptote. So we're going to have solution curves that probably look something like this. And then above, we're going to have solution curves diverging away. So just based on this phase line, I would expect the solutions to look like this. So the b over a squared is definitely unstable because everything's diverging away from it. The 0 point, the top half looks definitely stable. Everything's approaching it. And usually we want to check the bottom half. Do we get stuff approaching it, or do we get stuff diverging away from it, which would imply semi-stable? But since nothing exists down here at all, I think it's safe to say that this is stable, because all the solutions that exist that are nearby this point are approaching y equals 0. Semi-stable would imply that some solutions are approaching and some solutions are diverging away. We can see that there's some solutions approaching, and since there aren't any solutions that are diverging away, I think it is safe to say that this is stable equilibrium. Any questions on that so far? And you mentioned the professor was also talking about looking at the second derivative, y double prime. So let's take a look at that as well. If we want to know y double prime, and what information would that give us? What do you know about a graph if you know its second derivative? Like first derivative tells you slope and where the critical points are. What does second derivative tell you?
It would tell you concavity.
Yeah, you can check whether it's concave up versus concave down. And also wherever the second derivative is 0, you can expect an inflection point. So to calculate the second derivative, The notation I've been seeing here is if you treat y prime as just y single prime as f of y, then y double prime is going to be the derivative of that, not with respect to y, but with respect to t. And that means we're taking a derivative of a function with a function inside it, because y itself is a function of t. So how do you take the derivative of a function within a function?
It will be chain rule?
Yeah, we use the chain rule. We take the derivative of the outermost function f as if it was just with respect to y. And then we multiply by the derivative of what's inside with respect to t. So this is how we would apply that derivative here. The derivative of the outermost function with respect to the variable in question, multiplied by the derivative of what's inside with respect to the variable we're actually differentiating with respect to. So df dy times dy dt. If it helps, you could sort of imagine the dy is canceling out. So we really are taking df dt. To fill that in though, we can say y double prime equals df dy, which we can calculate here. We can just take the derivative of this function, ay minus b squared of y. Derivative of ay with respect to y would just be a. Derivative of b square root of y would be 1/2 times y to the negative 1/2. So that'll be b over 2 root y. And then that whole thing times dy dt. But we already know dy dt equals ay minus b root y. The f of y we had earlier. So this is derivative of f with respect to y times dy dt, which is the same as just f of y. Because dy dt, the whole point of f of y is the original differential equation was dy dt equals f of y. So if we want to find any inflection points, any points where y double prime is 0, we just need to check where this is 0. And note that that's a product. So you can check where is df dy 0, see if there's any new y values that make this whole thing 0. And also f of y being 0, we already know where f of y is 0. That's 0 at y equals 0 and y equals b over a squared. So we just need to check this extra df dy. Where is a minus b over 2 root y equal to 0? That'll tell us where the inflection points are. So how would you solve that for y?
Let's see. You add the b over 2 square root y to both sides and then multiply the 2 root y and then I squared. Yeah.
Yeah, then we should be able to just divide by 2a and then square both sides. And we could pull the 2 out of that as 4 because we're squaring it. So b over a squared divided by 4. And note that that introduces a new point of interest. We get a value 1/4 of that b over a squared. And that's not a critical point. That doesn't change the fact that this entire interval is still decreasing. But that gives us a new value, some new values to check for concavity. We want to now take a look at this region between 0 and b over a squared divided by 4, and this region and this region. So that now gives us 3 regions we want to check for concavity. So in each of those 3 regions, check the value of this whole thing and check whether it's positive or negative. And that'll tell you in these 3 regions, should you expect concave up or concave down? Any questions on that? So try running the numbers there. I mean, you don't have specific numbers, but you can still use the idea of maybe plugging in, if you imagine plugging in a very small number, like just a little tiny bit more than 0, what happens to this? Or if you imagine plugging in an enormous number, or somewhere between b over a squared over 4 and b over a squared. You could even make up some examples, like maybe half of b over a squared. That's definitely between b over a squared and a fourth of b over a squared. So you could actually plug in half of b over a squared and see what you get. Or maybe plug in an eighth of b over a squared. That'd be down in this region. Or plug in 2 times b over a squared. That'd be in this region. So try plugging in those values and check, do you get a positive number or a negative number? That'll tell you whether these regions are concave up or concave down. And that gives you a better idea of how the graph should be shaped. Any other questions on that? All right, then I will see you next time.